Okay, we rotate another integral. This one's from the UNSW integration B 2020 semifinals round 1 problem 2. We have the integral from 0 to 1 of x to the m of ln x to the n dx. Okay, I'm actually doing this one a second time because the first time I did it, I did this using the gamma function. That's probably my preferred way to do it. And I also did a really similar problem from, I think, the UK integration B, like almost the same thing. But what I wanted to do today was something different and try to do this using integration by parts. So to get started with this, what I want to do is let's just do the DI method for integration by parts over here to the right. And what I want to do, I definitely want to differentiate natural log x because that's going to be hard to deal with as an integral. So let's differentiate ln x to the n, and I'll integrate x to the m. And when we do this, I think I'm just going to do it one time. So when we differentiate natural log x, first we have power rule. So we have n ln x n minus 1. And then with chain rule, we're going to have like a 1 over x come out. And then integrating x to the m, again, power rule, this is x to the m plus 1 over m plus 1. Now we can evaluate part of this on the diagonal here. So what's going to happen, we're going to have this natural log x to the n times this stuff, x to the m plus 1 over m plus 1. And we're evaluating from 0 to 1. Well, first when we evaluate at 1, natural log of 1 is 0. This is just going to be some finite number like 1 over something. So this is clearly going to 0 for the first part. For the second part, it's a little more complicated because we end up with an indeterminate form. This x term is going to be 0, but here you plug in a 0, you get minus infinity to the n. So I think what I want to do for this is look at the limit really quick if I can. So the 1 over m plus 1 is not going to matter. It's a constant value. It's not going to affect the limit, but I'll just bring it up front for now. And we're evaluating 0 from the right side, so I'll write this as 0 plus. And I'm going to actually skip writing it this way because we already know this is going to be an indeterminate form. We're going to have this infinity times 0, and we can't do anything with that. But if I write it as a fraction, so if I write this as ln x to the n, and then bring this into the numerator, or sorry, bring this into the denominator as x to the minus m minus 1, then this is actually set up for L'Hopital's rule. Because now that we have a negative exponent on this, we're going to have this condition here that I think m is greater than 0 and n is greater than 0. So knowing we have a negative exponent here, the denominator is going to infinity. We don't really know if it's positive or negative infinity in the numerator just because we don't know if n is odd or even. So then with L'Hopital's rule, we'll go ahead and take the derivative. I'm just going to remove this because it's not going to affect our limit at all. So we'll just deal with this piece right here. So when we take the derivative on this, derivative here in the numerator, that's going to be n ln x. We basically just did it right there, right? And then I'm going to take the chain rule, the 1 over x, let's bring that into the denominator. And then the derivative of this is going to be minus m minus 1 x minus m minus 2. But then we have the same base here, x times x. If I multiply these together, I can just change this one to minus m minus 1 again. And then I'm going to go ahead and remove constants again. And one thing I should say about that, sorry, is you really shouldn't do this normally. You shouldn't do this if you want to find out exactly what the limit is. I'm doing it with the assumption that I'm going to get either 0 or infinity. And so for those values, the constants aren't going to matter. So really, I'm trying to show that this limit's going to be 0, and that's why I'm just discarding constants. But if like the limit was going to be 5 or something, you'd really want that because then the constants would change the value. But I'm kind of just doing a shortcut here. And so what I'm trying to show here is when we did L'Hopital's rule, you'll notice we still have the same denominator. The numerator has changed because we changed this power on the exponent. If we did this again, basically the same thing would happen again. So doing again, we still have the same denominator. We'd have constants that I just erased because they're not going to change anything. But then notice this exponent is decreasing. So it may look like you're doing L'Hopital's rule forever, but actually that's not the case because n is just some finite value. So eventually, if we do L'Hopital's rule, like I guess n times, eventually let's say this exponent's going to be 1. And then now at this point, this is still an indeterminate form, but if we do it one more time, now the exponent on this is actually 0, and then this is actually 1. But then if that's the case, we can actually bring this back into the numerator, and we just need to evaluate this limit of this in the numerator. It's just going to be the limit of x to the m plus 1 now. But when you plug 0 in here, this is just going to be 0. So after that whole discussion, we just get that this is 0 and this whole piece is 0. So what that means is we just need to deal with this row here. We just need to deal with this as an integral. Okay, so now putting this together as an integral, we'll notice we have a few constants that I'm going to bring out front of this. So we have this n plus 1, and the minus sign too. So what we'll do is we'll write this. So what I'll do is write this as minus n over m plus 1, and then we have the integral going from 0 to 1. But I can combine the x's. I can divide this x into this and subtract off 1. So we're going to end up with natural log of x n minus 1 times this just x to the m dx. And now at this point, just notice the similarity between what's left and our original integral. Very similar, but the only difference is this exponent over here. So what I can do for this to kind of bring it all together is let's put a label on the original one. Not just I, but we'll call this specific, because the m, so this is not really changing, but the thing that's changing is going to be this n. So I'm going to call this I sub n here. So for this thing right here, we can call this one I sub n minus 1. And so that's going to give us a recursion formula, a way to equate this to this. So what we can say about this is I sub n is going to be equal to this constant in front minus n m plus 1 times I n minus 1. But now if you think about doing this repeatedly, we can then get a value for I sub n minus 1. What's going to happen, it's going to have the same form, but instead of pulling out an n now, you're going to be pulling out this n minus 1. So we're going to have minus n minus 1 now. Over the n plus 1 is going to be the same. And then you're going to reduce the power on this by 1. So for the next value, you're going to have I sub n minus 2. So you can take this and plug it back in here. But what's going to happen when you do this? So after doing this over and over and over again, what's going to happen is you're going to have something like minus n. You'll have like this first one, minus n over m plus 1. The second one's going to be this, minus n minus 1 over m plus 1. Then you'll have a minus n minus 2 here. And then eventually what's going to happen is this last one is going to get down, because n's finite, so eventually we're going to get down to minus 1 over m plus 1. And then on the end of this, you're going to have this final thing, you're going to have I sub 0. But coming back to our original formula, we can actually figure out what I sub 0 is, just plugging 0 in for n. So this is going to be the integral from 0 to 1, x to the m, but when n's 0, this piece right here just becomes 1. So we're just integrating x to the m dx. So let's just do this really quick. This is just going to be power rule x to the m plus 1 over m plus 1. At 0, it's 0, and I didn't give myself enough room, but we're evaluating from 0 to 1. But when you plug in 0, it's 0. You plug in 1, it's just 1 over m plus 1. So here for our I sub 0 value, I'll just replace that and plug in right here a 1 over m plus 1. So I think from here we can put this expression together in order to finish it off. So notice everything except for this last one has a minus sign on it. So what's going to happen is it's going to be either minus 1 or plus 1 based on if n is odd or even. So in order to express all those minus signs, we can just write that as minus 1 to the n. And then if you ignore the sign, n times n minus 1 times n minus 2 all the way to 1, that's the same thing as n factorial. And then just notice everything in the denominator is an m plus 1. This right here, all the way to this point, this is n terms, right? As we start with n, go all the way to 1. But we added one more term right here, one more copy of 1 over m plus 1. So what that means is all this is going to be m plus 1 to the n plus that one. So we can write the exponent as n plus 1. And so for my final solution to this, we just have minus 1 to the n times n factorial over m plus 1 to the n plus 1, and that's it. Okay, there it is. Good one from UNSW 2020. Thanks everyone for watching. Have a good day.